In Part 1 of the multi-engine landing lesson, you learnt about the landing climb regulations and the landing distance regulations. In Part 2, you will learn a few more regulations and how to actually calculate the landing performance using sample data from an aeroplane flight manual.
Having discussed the regulation requirements, detailing the maximum landing distance that must be available at a destination airfield or alternate airfield, we will now examine in detail the regulations governing how the landing distance is calculated given non-standard conditions. In CAP 698, Section 3 on page 17, under point 511b, we read that if the runway is of grass up to 20 centimeters high, the landing distance should be multiplied by a factor of 1.15. This would effectively increase the landing distance by 15%. Point C states that if there is an indication that the runway may be wet at the estimated time of arrival, the landing distance should be multiplied by a factor of 1.15. Again, multiplying the calculated landing distance by a factor of 1.15 will increase the landing distance by 15%. Point D states that the landing distance should be increased by 5% for each 1% downslope. This means that for a 1% downslope, the landing distance should be multiplied by a factor of 1.05. Therefore, for a 2% downslope, the factor would be 1.1. Point D also states that no allowance is to be permitted for upslope. The reason for this is that upslope will reduce the landing distance. If a pilot were to ignore the reduction in the landing distance, then a margin of safety would be incorporated into the landing distance calculation. Lastly, point E states that there must be compliance with the dispatch rules for scheduled or planned landing calculations, and that these can be found in JAR Ops 1.550 paragraph C. The dispatch rules found in JAR Ops 1.550 paragraph C state that for dispatching an aeroplane, it must be assumed that, firstly, the aeroplane will land on the most favorable runway at the destination airfield in still air, and, secondly, that the aeroplane will land on the runway most likely to be assigned, considering the probable wind speed and direction. If this second assumption cannot be met, the aeroplane may be dispatched only if an alternate aerodrome is designated, which full compliance of the regulatory dispatch requirements can be met. These dispatch regulations may sound a little complicated, so let's examine them further. The first assumption is that the aeroplane will land on the most favorable runway in still air or zero wind. This means that, assuming zero wind at the destination airfield, the runway which would accommodate the largest possible mass would be selected, since that is the most favorable runway. In our example on screen, assuming zero wind, runway 04 and runway 22 both allow a maximum landing mass of 1,500 kilograms. But runway 31 and runway 13, being much shorter runways, allow a maximum landing mass of only 1,000 kilograms. Therefore, the most favorable runway in still air is either runway 04 or runway 22, which both allow a maximum landing mass of 1,500 kilograms. The second dispatch assumption is that the aeroplane will actually land on the most likely runway to be assigned considering the probable wind speed and direction. In this case, runway 04 has a strong headwind for the landing, which will allow the aeroplane to land at a much greater mass than if there were no wind. In our example, the headwind has increased the maximum landing mass to 1,750 kilograms. However, runway 22 has a tailwind, which will decrease the maximum landing mass to 800 kilograms. Runway 31 and runway 13 both have a full crosswind. Therefore, the maximum landing mass for these two runways will be the same for still air. If the second dispatch assumption is that the aeroplane will land on the runway most likely to be assigned considering the probable wind speed and direction, then it would have to be the runway 04 with a maximum landing mass of 1,750 kilograms. In summary then, the first assumption requires that the pilot select runway 04 or runway 22 for a maximum still air landing mass of 1,500 kilograms, and the second assumption will require the pilot to select runway 04 for a maximum landing mass of 1,750 kilograms. Now we need to consider what to use as the dispatch mass of the aeroplane. If the aeroplane was dispatched at 1,750 kilograms, and then, on arrival at the airfield, the wind was less than forecast, the aeroplane would not be able to land. Therefore, the aeroplane must be dispatched with a mass of 1,500 kilograms. Dispatching the aeroplane with this mass would mean that, no matter what conditions prevailed at the destination airfield, the aeroplane will have a mass that will allow it to land at the airfield. The way to simplify the dispatch rule is always to consider the greatest mass in still air and the greatest mass in the forecast wind conditions, and, of the two, take the lesser mass as the dispatch mass. Of the two, it is the still air mass that is usually the lesser mass, as shown in our example. The exception is when there is a tailwind on a unidirectional runway. A unidirectional runway is a runway whose direction for takeoff and landing is fixed in one direction. And in this case, the maximum landing mass in the tailwind will be less than the maximum landing mass in still air. This part of the lesson will deal with how the aeroplane's landing distance can actually be calculated. All aeroplanes will either have a pilot operating handbook or an aeroplane flight manual. The purpose of these manuals is to show not only how to operate the aeroplane, but also to detail the aeroplane's performance. Shown on screen is an example of the landing performance information. The example graph we will use is figure 3.9 on page 21 of section 3 in CAP 698. Always take a look at the associated conditions first, paying particular attention to the power and flap settings as shown here. Also notice that this graph assumes a runway which is paved, level, and dry. If the runway conditions required for a given calculation are different, corrections will need to be made to the values that this graph will give. We saw these correction factors earlier. Notice this area here, which highlights the obstacle height speed for different weights. This is actually the reference landing speed. The regulatory speed at the landing screen height is called VREF, and, for Class B multi-engine aeroplane, it had to be no less than the greater of VMC, or 1.3 times the stall speed in the landing configuration, 1.3 VSO. A pilot must adhere to the VREF speeds shown here because they are the speeds that have been used to construct this graph. If a pilot were to deviate from these speeds, then the required aircraft performance would not be achieved. Having looked at the various bits of information associated with the graph, let's now examine the graph itself. The left-hand carpet of the graph involves the variations in temperature and pressure altitude. This part of the graph accounts for the effect of air density on the landing distance. In the example, we will assume a temperature of 5 degrees Celsius at a given airfield situated 4,000 feet above mean sea level. To use the graph then, move upwards from 5 degrees Celsius until you have reached the 4,000 feet pressure altitude line. Then move right until you meet the reference line, shown here. The next variable is mass. In our example, let us assume a mass of 3,400 pounds and a VREF of just below 80 knots. From the reference line, we must move down using the sloping guidelines until we reach 3,400 pounds, as shown here. From this point, we go horizontally to the right until the next reference line. The next variable is wind. In our example, we will assume a 10-knot headwind. Notice, though, that the slopes of the headwind and tailwind lines are different. We therefore recognize that the 150% tailwind and 50% headwind rules that you learnt about in the General Principles for Landing lesson have already been applied. Travel down the headwind line until you reach 10 knots headwind, and then move horizontally right once more, up to the last reference line. Remember that the landing starts at the 50-foot screen height. So from this point on the graph, we must move up the sloping guidelines to the end. The landing distance in our example then is approximately 2,000 feet from the 50-foot screen to the full stop. The landing roll, in other words, the ground section of the landing, is just 990 feet. Let us now assume that the runway has a grass surface and that the grass is wet. Remember that both these variables cause an increase in the landing distance. Since the graph assumes a paved, dry runway, we will have to make a correction to the landing distance for the different conditions. You may recall that grass increases the landing distance by 15%, or by a factor of 1.15, and a wet surface also increases the landing distance by 15%, or by a factor of 1.15. Our calculated landing distance is 2,000 feet, but correcting it for grass means we will need to multiply this by 1.15, and again by 1.15 because the grass is wet. This now makes the landing distance 2,645 feet. Let us now assume that the runway has a downslope of 1%. You may recall this would increase the landing distance by 5%, or by a factor of 1.05. This now makes the total gross landing distance 2,777 feet. To comply with the regulations, you may recall that the landing distance must be within 70% of the available distance at the airfield. Therefore, multiply 2,777 by 1.43. This means that our landing distance available must be at least 3,971 feet. Before this lesson ends, let us briefly look at the pages in CAP 698 regarding the multi-engine Class B aeroplane for landing. Page 17 and 18 of Section 3 detail the landing distance requirements and climb gradient requirements that we mentioned already. Near the top of page 18 is an example of how to calculate the one-engine out gradient using figure 3.7. The bottom half of page 18 is another example of how to calculate the climb gradient, but this time using all engines operating, and it refers to figure 3.8. Work through these examples, and especially on how to change a rate of climb into a gradient, because the two graphs used in these examples do not directly provide a gradient. It must be worked out. Page 19 is the landing climb graph, figure 3.8. This graph assumes both engines are operating. Again, this graph only provides you with the rate of climb. If you need to calculate the gradient to check whether you meet the all-engine climb gradient requirement, then you must convert this rate of climb to a gradient. If you are unfamiliar with this conversion, either work back through the examples of the previous pages which we just mentioned, or else consult previous lessons in the General Performance Principles section. Page 20 is an example you can work through, which is about how to calculate the landing distance required, and this example uses the normal landing distance graph shown on the next page, page 21, as shown here. On page 22, there is one more example, but this time, this example is how to calculate the maximum landing mass. This example uses a graph on the next page, which is the short field landing distance graph. Hopefully, you are now able to work through the landing graphs for Class B multi-engine aeroplanes and make the corrections to the graphs for any conditions that are not accounted for by the manufacturer. If you need further practice in using the graphs to increase the accuracy of the results, we suggest that you work through the examples in CAP 698 that we just mentioned, or to use the questions which test you on what you have learnt in this lesson. That concludes the section on Class B multi-engine performance. The next section of aircraft performance will focus on the Class A medium-range jet aeroplane.